Hey guys, in this video we're going to explore two binomial expansions exercises which tend to confuse students a bit more. They are trickier, harder examples or exercises. In this case we have the following. Find the term in x to the negative 3 in the expansion of a product of two binomials. This is a classic IB math style exercise, one that showed up many times in IB math exams. Now, the second exercise is one that involves the complexity of it, is mixing binomial coefficients, expansions, and also arithmetic series. So that's what makes this second exercise a bit more complex, mixing these two topics. Now, let's tackle these two exercises. In x to the negative 3, in the expansion of a product of two binomials, x minus 1 cubed times 1 over x plus 2x to the 6th power. When you have this type of question in IB math exams, one of the binomials will be a simpler one. And in this case, I am, of course, referring to x minus 1 cubed. Now, this expansion can be done quite fast. If you remember the third row of Pascal's triangle, which we can see right here, 1, 3, 3, 1, we can use it to expand x minus 1 cubed. So we have 1, 3, 3, 1. We have x cubed, x squared, x, and x to the 0. And we have negative 1 cubed, squared, now from right to left, to the first, and to the 0th power. Therefore, this whole expansion can be simplified to x cubed minus 3, x squared plus 3x minus 1. Now, this is for me to say that within this exercise, at least one of the binomials will be a simpler one. So let's already replace this x minus 1 cubed by this. And now let's focus on the second part. What I want you to realize in this expansion is that as you're expanding it, the powers of x will jump, which means increase or decrease depending on the order that you choose, in steps of the difference between the exponents. We have x to the first power and x to the negative 1. So they're going to skip in steps of 2. Now, what am I trying to say here? What do I mean by this? If you write the first few terms, and let me just write the first 3, you realize just that. You notice that after simplifying these terms, which give you 1 over x to the 6th, which by the way is the same as x to the negative 6. The second one gives us 12 over x to the 4th, which is the same as 12 times x to the negative 4. And the third one gives us 60 over x squared, which is 60x to the negative 2. Now we can spot a pattern here. These exponents are increasing with a common difference of 2. Until we get to the last one, which is 64x to the 6th power. So we can see that the powers of x range from x to the negative 6 to x to the 6th power, which tells us that to produce terms in x to the negative 3, we need to make combinations through these multiplications, which, well, will give us x to the negative 3 as a result. And the combinations are the following. 3x times whatever this term is, which we're going to find in the next step, or x cubed times this term, which we're going to find as well. We actually did find this one or these ones, but we're going to find them again, just for the sake of this explanation. Now, what is this first one? This is our 6 choose 0 times 1 over x to the 6th times 2x to the 0, which is just 1. What is the second one? This is 6 choose 1 over x to the 5th power times 2x to the 1st power. Now, creating these products gives us, and by the way, just simplifying these before, we have 1 over x to the 6th and 12 over x to the 4th power. Now, the product in purple gives us x cubed times 1 over x to the 6th, which is 1x to the negative 3. Now, the second one gives us 3x times 12 over x to the 4th, which is the same thing as 36x to the negative 3. Therefore, the term in x to the negative 3 is x to the negative 3 times 1 plus 36x to the negative 3, which is 37 times x to the negative 3, which, by the way, is the same thing as 37 over x cubed. All right, so that's all there is to this exercise. If you wanted to expand the whole binomial 1 over x plus 2x to the 6th to see this foiling process, you could. if this power is not that high. Now let's jump to the next exercise. Now on to the second and last exercise. The coefficients of x to the k plus 1, and x to the k plus 2 in the expansion of the binomial 1 plus x to the power of 23, they form an arithmetic sequence. Determine the possible values of k. Now we are mixing binomial expansions with sequences in series, which definitely makes for an interesting exercise. As we know, as we expand a plus b to the power of n, the structure of this expansion will be the following: n choose 0, a to the n minus 0, which is just a to the n, b to the 0, which is 1, plus n choose 1, a to the n minus 1 times b to the first power, which is just b, plus n choose 2, a to the n minus 2 times b squared, plus dot dot dot. Now this is a general form or formula for a binomial expansion. As we apply it to the scenario that we have, meaning 1, this 1 over here is equal to a, so let's substitute it right here, and b being equal to x, let's substitute it here, and let's write also the last two terms in this expansion. N choose n minus 1, 1 to the n minus n minus 1, which is 1 to the 1, times x to the n minus 1, and the last one, n choose n, 1 to the 0, which is just 1, x to the n. So this is us applying the scenario that we have, the binomial that we have in the binomial expansion using the binomial theorem. Now let's take a moment to notice a few things. All these 1s to whatever power we have, n minus 1, n minus 2, they're all going to be 1. So this is 1, this is 1, all of them, they're all equal to 1. So we could reduce this binomial expansion to n choose 0, and if you want to put an x to the 0 here, that's fine as well, plus n choose 1, x to the first power, plus n choose 2, x squared, plus dot dot dot, n choose n minus 1, x to the n minus 1, plus n choose n, x to the n. Now the exercise is stating that the coefficients of x to the k plus 1, and x to the k plus 2, they form an arithmetic sequence. Do notice also that the only contribution that we have for the coefficients are these binomial coefficients, because in all of these terms, in all of them, there will not be any integer, any number which multiplies these binomial coefficients. Therefore, the only contribution for a specific number is from these individual binomial coefficients. And also we can replace the exponent in our expansion by 23. We are raising 1 plus x to the power of 23. Therefore, this is what we have: 23 choose 22, and then finally 23 choose 23. Now here's the link between this binomial theorem exercise with sequences in series. We know that x to the k plus 1, and x to the k plus 2, they will show up somewhere in the middle of this expansion. We don't know exactly where, but they will show up. And given that the coefficients, they form a arithmetic sequence, and the coefficients are composed only by these binomial coefficients, the difference between these will be the same as the difference between these. That's the basis of an arithmetic sequence. The difference between two consecutive terms is equal. It's identical as we move along the sequence itself. Therefore, 23 choose k plus 1 minus 23 choose k plus 1 minus 23 choose k should be equal, if this is an arithmetic sequence, to 23 choose k plus 2 minus 23 choose k plus 1. Another way of writing this is 2 times 23 choose k plus 1 equals 23 choose k plus 23 choose k plus 2. Now going back to the definition of a binomial coefficient, what is n choose k? This is n factorial over k factorial times n minus k factorial. Now applying this to the binomial coefficients that we have, we get 2 times 23 factorial over k plus 1 factorial times 23 minus k plus 1 factorial. And this equals, applying to the other two coefficients, it equals this. Now we can simplify all these 23 factorials because, well, we can just divide the whole equation by 23 factorial, so we end up with lots of ones here, here, and here. We can also rewrite this as 22 minus k factorial. We can rewrite this as k plus 1 times k factorial. Same thing over here, k plus 2, k plus 1 times k factorial, and this guy as 21 minus k factorial. So let's rewrite this equation again. We have 2 over k plus 1, k factorial, 22 minus k factorial equals 1 over k factorial, 23 minus k factorial, plus 1 over k plus 2, k plus 1, k factorial times 21 minus k factorial. We can also simplify all these k factorials, which will be equivalent to multiplying the whole equation by k factorial. But we can simplify this even more. We can rewrite this 22 minus k factorial as 22 minus k times, and we subtract it by 1, 21 minus k factorial. Same idea over here, 23 minus k, 22 minus k, 21 minus k factorial. Remember, whenever we stop, we can place a factorial towards the end or at the end. And the idea behind this simplification is the fact that, well, let me use 6 as an example. Given that 6 factorial is 6 times 5 times 4, 4 times 3 times 2 times 1, you can rewrite 6 as 6 times 5 times 4 factorial, given that all these numbers, this product, is already represented by this 4 factorial here. And after writing the fractions, the quotients like this, we can also simplify the 21 minus k factorials that show up. Now, you can simplify this a little bit more if you write everything with the common denominator, or you can use your GDC, either the numeric solver or by graphing, to come up with the 2 possible solutions, And the solutions are k equals 8 or k equals 13. And I think it's worth mentioning what these represent. If k is equal to 8, that means that the terms in x to the 8, x to the 9, and x to the 10, they form a arithmetic sequence. And if k is equal to 13, then it's the coefficients in x to the 13, x to the 14, and x to the 15 that form an arithmetic sequence. And which one is correct? Well, they're both correct. Both of these scenarios will show up in the same expansion. And let's look at the expansion using a software so we can see which coefficients we're talking about. So this is the expansion of 1 plus x to the power of 23. If you analyze the coefficients in the terms x to the 8, x to the 9, there's a 9 here, this is the exponent of this guy, let me fix this, and x to the 10, the coefficients being 490,000 and 817,000 and 1,144,000 and change. As you calculate the difference between these numbers, you see that it's a common difference, and the difference, it is equal to 326,876. And if you do the same with this, and this, first of all, you realize that the numbers are exactly the same, but in the opposite order. Therefore, the difference over here is negative 326,876. Now that is it.